Hey guys, today I am going to share a video with you on isotopes, and I am going to teach you about the isotopes of hydrogen and also how we can designate isotopes, how we can write symbols for isotopes, and also tell how many protons and neutrons and electrons there are in an atom of a specific isotope. So I will just go ahead and get started. Wondering how close I am to the screen right now in my Mario outfit. Okay, that's enough. I'll go ahead and get started. So, when we think about the atomic nucleus, we know that in the middle, in the atomic nucleus, we have protons and neutrons. It is only the atomic nucleus that is different for isotopes. So, I feel like I'm getting ahead of myself a little bit. So except for the simplest hydrogen atom, all atomic nuclei are composed of protons and neutrons. And if you haven't read or seen my video in which I talk about positive Patty proton and nerdy Nelda neutron and enraged Elliott electron, I would encourage you to watch that video if you have access to that video from me, because it sheds some light on the composition of the atom and those particles that can be found in it. So by definition, a proton has a positive charge. It is equal in magnitude to the negative charge on an electron. A neutron is a neutral particle, and it is the number of protons that determines an atom's identity. For example, 3 is the atomic number for lithium, and any atom with 3 protons in it is lithium. So I'll just review that the atomic number is the number of protons in an atom. Now, when we look at the masses of protons and neutrons and electrons, you can see that the mass of a proton and a neutron is about the same, and it's very, very, very small when you look at it in grams. This isn't a very handy way to think about the mass of atoms and elements on such small scales. So in a video, in a future video to come in which I talk about atomic mass, I will address that issue at that time. But if you look, we can say something about this. They're approximately the same as each other. So a proton and a neutron both reside in the nucleus, and they're about the same size as each other in terms of mass. I shouldn't say same size. They have the same mass. And I'm not positive about their size. I could look it up, but I'm not positive at this point. An electron, its mass is so, so, so tiny. It is negligible compared to the bulkiness, the bigness, the massiveness of the protons and the neutrons. So by definition, isotopes are atoms of the same element that have different masses or different numbers of neutrons. Since it is the protons and neutrons in an atom that contribute to the mass, then it is really the nucleus that determines the mass of an atom. So I'm just going to review very quickly positive Patty proton and nerdy Nelda neutron and enraged Elliott electron, because there is a good chance that I refer to protons as positive Patties and neutrons as nerdy Neldas and electrons as enraged Elliots, and I don't want you to think that I'm going crazy if I don't at least preface it with an explanation as to where this originated. So I told a story in class about Matterville, and in the middle of Matterville there is something called the Nucleus Arcade. In the Nucleus Arcade resides sisters. One is positive Patty proton, who is a robust girl with a very positive outlook on life. That is a smile, by the way. and eyes that sparkle. She's very optimistic, always pleasant to be around, and I suppose I ought to give her some hair. I do not have the same level of control that I have on a whiteboard right now with this writing thing that I'm using. Okay, also in the Nucleus arcade is Nerdy Nell the Neutron. Nerdy Nell the Neutron is also robust, and she has a blank stare with no expression on her face. I will give her some hair, but she doesn't express emotion one way or the other. Completely emotionless and doesn't show any indication of having positive thoughts or negative thoughts. Okay, so Nerdy Nell the Neutron is neutral. Positive Patty, Proton is positive. All right, the Nucleus arcade. Now, the thing is, under ordinary circumstances, these two, and if they have any more sisters, they're stuck there. So, under ordinary chemical reactions, the composition of the nucleus does not change. Okay. Around the Nucleus arcade are electron roadways. And on the electron roadways exists a fella by the name of Enraged Elliott Electron. Enraged Elliott Electron rides on his chrome-plated Harley Davidson, and I will just try to draw it here. I have a feeling this is going to be a doozy. So we need a wheel and another wheel and some big handlebars and maybe a gas tank. Oh my goodness, this looks like a tricycle. This is going to be my chrome-plated Harley Davidson. And you can see that I am drawing Enraged Elliott Electron, very tiny. And he would have this itty-bitty head. But I want you to see what his face looks like. So I'm going to make a caricature of his face. And I'm just going to blow this up a little bit. So caricatures are those images where the head is really, really big and the body is drawn small. So that's what we're seeing right here. So he has squinty eyebrows and enraged, negative disposition. He is full of angst, and he rides around on these electron roadways. So when I refer to electrons, protons, and neutrons as positive Patty Proton, Nerdy Nell the Neutron, and Enraged Elliott Electron, this is where it's coming from. There is more to the story, but this is what I need for this. So just to review, they're in the nucleus, they're bigger. All of the mass in the nucleus is coming from here, not out here. Enraged Elliott is so skinny and so small and has such a negligible mass that it just doesn't matter. Okay. So let me review. Atoms of the same element have different masses or different numbers of neutrons. The protons and electrons are the same in each atom of the element. The only thing that's different is the number of neutrons. Also, the chemical behavior is the same for all isotopes of an element. And if you have a sample of any element, it contains all of those isotopes in different percent abundances. So these are some of the symbols that we use for the subatomic particles that you will see me frequently using throughout the year. And P with a plus sign for protons, N with a 0 for neutrons, and E for electrons with a negative sign. Now, I would like you to refrain from making your neutron symbol represented by this. I've seen this before where people put a plus and a minus together, indicating, oh, they cancel each other out. I would rather you not do that and just cross this off. This is an N. And just use a 0, indicating no charge. I don't want to give any indication that there's pluses and minuses there that are canceling each other out. So we'll just use an N with a 0. Okay, by definition, the atomic number is the number of protons in the element and identifies the element. With the mass number, we are talking about a specific isotope of an element. And the atomic mass is a weighted average of all known isotopes of the element. So the mass number is referring to the number of protons plus the number of neutrons in one isotope of an element. So when we remember positive patty proton and nerdy null neutron and their massiveness, their robustness, each of them has, let's say, a mass of 1. So if I have 3 positive patty protons and 4 nerdy null neutrons, 3 plus 4 will equal the mass number, which would be 7. The atomic mass is a weighted average of all of the known isotopes, and a future video will explain how to calculate an atomic mass and how the different types of isotopes are taken into account when that's being calculated. All right, so there are 3 isotopes of hydrogen that are relatively the most abundant. I think there are 7 total that are known, but these are the 3 that we're going to talk about. The simplest hydrogen atom is called protium. Uh-oh, whoops-a-daisy. I gotta engage my pen. And I want to change my pen color to black. Uh-oh, I changed it to white. That is not going to work on this screen. All right, black. All right, 3 things. I don't even know what I'm talking about. I'm going to draw the nucleus of each of these hydrogen isotopes. Now, one thing about the nucleus is that since this is hydrogen, they will all have 1 proton. And if this is a neutral atom, there will be 1 enraged allyl electron in that first energy level of the atom. Okay, so the numbers of protons and electrons stay the same for each isotope. Now the thing that's different is the number of neutrons. Protium is the most common type of hydrogen atom. In a sample of hydrogen, 99.985% is protium. It has 0 neutrons. So the simplest hydrogen atom doesn't have any neutrons at all. Just positive patty sitting in there by herself. Deuterium has 1 neutron. So if protium has a mass of 1, we would say deuterium has a mass of 2. Tritium has 3 neutrons. Oh, I'm sorry, I totally screwed that up. It doesn't have 3 neutrons, it has a mass of 3. It has 2 neutrons. I'm going to make that as dark as I can. That is a 2 neutrons. So there are a couple of ways we can represent these 3 isotopes of hydrogen. One way is called hyphen notation. So the mass number, again, is the number of protons plus neutrons. So the mass number of protium is 1. Hyphen notation takes the name of the element, hydrogen, with a hyphen, and it's followed by the mass number. So that would be hydrogen 1. This would be hydrogen 2. And tritium would be hydrogen 3. Okay, so that is hyphen notation, a way to designate each of the 3 different isotopes of hydrogen. Another way to designate isotopes is called a nuclear notation. With nuclear notation, you have the element symbol and its atomic number right there. So these are going to be the same for each of these isotopes. Since they all have one proton, this will be the same. And right here is where the mass number goes. Hydrogen 2 has a mass of 2, hydrogen 3 has a mass of 3. So this is called the nuclear symbol. You'll see that there's a trace or a 0.015% of all isotopes or all hydrogen atoms are deuterium, and just a trace amount is tritium. Tritium is actually a radioactive isotope of hydrogen. Very trace amounts of it in any hydrogen sample. So, this slide just summarizes what I just wrote. It's a little bit neater. Excuse me. Uh-oh. I see that. I hope that I'm not clicking with this, because I am not going to have time to make a new video. I am noticing my microphone kind of wiggling and jiggling, and I hope it's, cross your fingers that it's not destroyed, because we're just going to have to deal with it if it is. I don't have time to make a new one. Okay, so this is just a summary of what I talked about in the previous slides, the two ways to designate isotopes with the hyphen notation and the nuclear symbol. So a nuclear symbol for uranium-235 is going to include the symbol, the element symbol, U. The atomic number for uranium is 92. And if it's uranium-235, that means it has a mass of 235. Now let's talk about protons and electrons and neutrons here. This number here is always going to give us protons, the number of protons. Now in a neutral atom, that's equivalent to the number of electrons. So we have 92 protons and 92 electrons. The atomic number is 92. To get the number of neutrons, we have to remember that all of the mass is in the nucleus. So if there are 92 positive protons, the remainder of this, if the nucleus has a mass of 235, the rest of them have to be coming from neutrons. Nerdy Nell does. So to get the number of neutrons, you just have to take the mass number minus the atomic number. And I will tell you that I am so bad at simple math that I need to physically write this out to get a number. And 13 minus 9 is 4, so there are 143 neutrons in an isotope of uranium-235. In a different isotope, you're going to have 92 protons and 92 electrons, but you might have different numbers of neutrons. No, you will have different numbers of neutrons in a different isotope of uranium. And this is just a summary, again, of the hyphen notation, the element name followed by the mass number, and the nuclear symbol. The element symbol with the mass number on top, the atomic number on the bottom, and there is an example of that tritium-hydrogen isotope. So, let's practice. If, and I have to just, I hope I'm not making scratchy noises. Trying not to bump the microphone. I need to refer to my periodic table to complete this, as do you, unless you have it memorized. And if you do, I would be highly impressed. All right. With each of these, we're giving a little bit of information, and we have to come up with the rest of it. So this is carbon-14. remember that if there's a hyphen, this is my mass number. So my mass number is 14. When I look at carbon on the periodic table, I see that its atomic number is 6. That means it has 6 protons and 6 electrons. I'm going to put the nuclear symbol together. The nuclear symbol has a mass number of 14. So what you see in the hyphen is the same as the top number in the nuclear symbol, and the atomic number goes on the bottom. Now remember, to get the number of neutrons, all we need to do is subtract the 6, the bottom number, from the top number. So in an isotope of carbon-14, the number of neutrons is 8. That's not the most common type of carbon. If you look on the periodic table, I see that the average atomic mass is 12.01. That means the majority of the atoms likely have a mass around 12. So it's likely that we could say that it's likely the most common isotope of carbon is carbon-12. All right, let's go to the next one. This is an element with an atomic number of 56 and 79 neutrons. All right, atomic number of 56. Again, I do not have the periodic table memorized, and I probably need some cheater glasses to see this better. I will have to hold it out, and you get to see me in prime form here. Element 56 is barium. I don't know which barium isotope this is yet, but I'm going to write this down before I forget. All right, if I have an atomic number of 56, I have 56 protons and I have 56 electrons. I don't know why I forgot to write the 6 there. Getting ahead of myself. The number of neutrons is 79. And if I start my nuclear symbol, my atomic number is 56, that has to go there. And my mass number, I need that. Mass number is going to be protons plus neutrons. Again, because I feel challenged at math, I need to go ahead and add this up manually. I have 56 plus 79, 5, carry the 1, and I have 135 neutron as a mass. My mass is 135. So it's barium 135. The mass number is 135, and that is what I put there. Okay, I would like you to try and fill in the blanks to the rest of these right now. So you should pause this and go ahead and fill in the blanks. Try these two with the information that's given, and the answers will show up on the next slide. I am hoping that you paused it and actually went through the problems to practice, because the assignment involves just this sort of practice. So if you need to get it from me, please come see me, and I will make sure you get it and explain some things before you start it. So the next video is on relative atomic mass. This concludes this video, and I hope that you learned something about isotopes and the isotopes of hydrogen. And that is all for now. I am over and out. Thank you for watching.